Okay, so stationary waves. Now, what is stationary waves? We can also say standing waves. Okay, standing waves. So what is it? Now, if you look at every instrument, by the way, if there's any lagging, let me know, because my line is not very good recently. I think it's because of the weather. So if it's lagging, if it started to lag, let me know. But I have the session recorded down. All right, so every instrument, they produce sound based on the concept of stationary waves. Okay, when you plug a guitar string, or when you play an organ, a piano, the sound that you hear, it comes as a set of frequencies. Okay, not one frequency, not two frequencies. It comes to you as a set of frequencies. Okay, let's take one example. Let's take the guitar strings. We are going to look at how does the stationary waves helps in producing sound, especially in the instruments. Okay, if you play any instruments, this is what happens. This is how the sound is produced. Now, first, let's take a guitar strings. Okay, so we know that a guitar strings is fixed at both ends. It's fixed at both ends. So since it is fixed at both ends, then if you look at the particle at the both ends, the particle cannot move because they are fixed, right? So here is the particle has no motion. Same with here, the particle has no motion. A point of no motion, we call it nodes, N-O-D-E-S, a point of no motion. Okay, now let's say if I plug the string, if I plug the guitar string, then I have created a vibration which created a wave on the string. Now this wave travels in the string, and once it reaches the other end, this notes, what happened to the wave? The wave, when it hit a fixed point, it will reflect back. Okay, same as if it hit a hard surface, it will reflect back. So the wave that you created reflect back, and that reflected wave will combine with another incoming wave that you created. So meaning that there are two identical waves. Why do I say identical? Because the reflected wave, it comes from the same source as well. So by plucking the string, first wave is created here, wave 1, and the wave reflect back. Here we call it the reflected wave, and this reflected wave will interfere with the incoming wave. Okay, because you have wave is like a continuous disturbance, right? Continuous. So the reflected wave will combine with the incoming. Okay, it's continuous. So meaning that over time they will interfere each other, and when interference happen, you learn about that one. What happens? They either go for constructive or destructive. Okay, they either go constructive or destructive. Now, what you will see, or the result of the combination of the wave is something like that. Okay, there are many patterns that can form. This is just one of it. This is just one pattern. So the string like this. Okay, and then you will see that the string will vibrate up and down like this. This one come down, this one go up. Okay, it goes like this. It's like, okay, the crest, if you look at the crest, this is the crest, this is the trough. What happened is that you will see this pattern where the crest and the trough just dancing up and down. Okay, it doesn't move. It stays there and it goes up and down, up and down, up and down. This is what you will see. This is one of the pattern that you will see. There are many more patterns that we will look at later. Okay, now, why do you see this? Understand that what you see here is due to the combination of two waves. Not one wave, is a combination of two waves. Which two? The one that you created and the one that reflected back. Since they are from the same source, they have the same frequency, they have the same wavelength, they have the same speed, so they can interfere constructively. Okay, now, so the result or the pattern that you see is the result of the combination of the original wave and the reflected wave. And also at any point on the string, it shows the combined effect of the two waves. It is never just one wave. At any point on the string, if I pick here, it is actually the resultant vector or the combined effect of the two waves. Now, this, you will realize that, you notice that a few points on the string, it will not move. It will not move in the sense that it will not go up and down. Okay, which 2 points? Of course, both ends cannot move because they are fixed, right? And then at the center, you will find that at one point at the center is also not moving. Over time, you see the strings like go up and down, but the point is not moving. It's like the point at the middle, it stays zero displacement, no displacement. Okay, but these two vibrate at a certain amplitude, amplitude. But this one, always it stays there, no amplitude at all. So what happened here is that we have created a point of no motion, just like the point at the both end. We call it, again, we call it nodes. So note, note, note. Now I have 3 nodes. This is just one of the scenario. Okay. Now, what happened to the node? What is actually happening at the node here? At the nodes, it's where destructive interference happen. Okay, so destructive interference, their amplitude cancel out, no displacement. And the crest and the trough here is, we call them antinode. Antinode. Same here. This is also antinode. Antinode is opposite to a node. It is where constructive interference happen. Okay, constructive interference, meaning that the two waves, they add up and then the resultant amplitude is 2 times, not 1 time, 2 times resultant amplitude. So if the wave has an amplitude A, then this is vibrating at 2A. This is vibrating at 2A. Okay, double the amplitude. So is it always node? This node always stays as a node, because over time the wave keep on moving, right? The wave is traveling inside the string all the time, but over time still they interfere destructive. Okay, that is why we call it a node. Okay, they always interfere destructively. But of course, we are not going to look at how they interfere. We are not going to draw all the pattern. That becomes very complicated. Okay, but you have to know that this is due to the combination of two waves that is traveling in the string. Okay, so this is the picture, is what you see here, is the combination. Now, why do we call it stationary waves? It's because the crest does not travel, the crest does not move. If you see the difference between progressive waves, progressive versus stationary. What is happening in progressive wave? The progressive wave is like normal wave lah. It travels, it travels. So if you have a string, you have a medium, you make a wave, and this wave will travel. The next second, it becomes here. The next second, it becomes here. So if you look at the crest, the crest here, after 1 second, it got here. After 1 second, it is now here. It is traveling on the same medium, meaning that as the wave moves, every particle will be raised, right? The first particle got raised. As the crest travel here, this particle raised. As the crest travel here, this particle again, it got raised. So as the crest is moving, every particle in the medium, they got raised up. So every particle get a chance to be the crest. This is an example of progressive waves. It is where the wave travels and every particle get the chance to be the crest. Okay, so energy travel in this example. How about stationary waves? Stationary waves like the one that we mentioned here in the string, the crest does not travel. This particle always be the crest. This particle always be the crest. The particle next to it does not get a chance to be the crest. Same here. The particle be the crest. All the particles here, they stay stationary. So the crest is not traveling. What happened to the energy in stationary waves? Energy, if the wave is not traveling, then the energy is stored. Okay, this one energy travel, this one energy store. That is how it produces sound wave. Now let me explain how it actually produces sound wave. You see, here, when the, okay, first thing, okay, let me draw it here on the right again, one more. I don't want to disturb this diagram. Okay, so this is our stationary waves. It vibrates up and down like this. Okay, so the crest does not move, only stays like this. Now, every time the string goes up, it will push the air particles. Okay, push the air particle as it goes up, and then every time it comes down, it will pull the particle, the air particle around the string. Okay, now this pushing and pulling, it creates compression and rarefaction. Compression, rarefaction. So meaning that this vibrating string, it produces compression, rarefaction, compression, rarefaction, compression. Same here, compression, rarefaction, compression, rarefaction, compression. What is happening here? The vibrating string, it produces a longitudinal wave, which travels, propagates, and come to us as a sound. This is how sound is produced on a musical instrument, like the strings instrument. Even in air column also works the same way. Okay, so sound due to vibration of strings, and not only just vibration, it is actually the stationary waves, which has twice the amplitude of the wave, that has enough energy to send the sound away. Okay, get the sound out. Right? Okay. So this is the basic idea of a stationary waves. Why do we call it stationary? Because the wave is not moving. It is storing energy on the medium. Okay, and that energy is being taken to vibrate the air particle around it and produce sound waves. Now, next one is we want to look at how many possible stationary waves can be formed if we pluck the string. Remember that I said this is just one pattern, right? So if I pluck the string, actually there are many patterns that can form. The first one and the most basic one is this one. The string goes, okay, note, note. The string goes up and then down like this. This is probably the most that you see, okay? The most common vibration. When you pluck it, you see this. This is the first stationary waves. The second one, okay, how do you know? How do you know the pattern? It's very simple. You just draw the wave out like this. I draw the wave and then like this. Now I put the pointer, note, 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 and note. You see, if you want to work out the pattern, you just find how many waves can be fitted between these two nodes. The first diagram, how many waves can be fit between these two nodes? How many waves is this? This one is half a wave, right? Because one full wave is sine graph, right? So if it's from here to here, then this is only half the wave. So this is half the wave can be fitted between these two nodes. All right, then you ask yourself, what is the next one? How many waves I can fit between these two, which is more than half a wave? You look at this diagram, this node and this node, right? You go to the next node, this one. So the first one and this node, how many waves in between the two nodes? This is one complete wave, which gives us the second stationary waves as this one. One complete waves, and then this is the vibrations. This one, I have created a node in the middle. So I have 3 stationary points. Okay, what is the next one? The next pattern. Then you go up again. I'm at here, right? So I go to the next node, this one. Okay, how many waves can fit between the first node and the current node? This is 1.5. So I draw the string. So 1.5, like this. This, and this. Okay, how many nodes do you have created? 2 in the middle, plus the 2 at the end. You can continue to work your way up to the next one, the next one, the next one, the next one. Okay, what is the next one then? We do 4, okay? Here we do 4 only. Okay, the fourth one is, then you go to the next node, which is this one. How many waves can fit between these two? 1, 2. 2 waves. So draw 2 waves inside like this. Now, this one, I have created 3 nodes in between. Total 4 nodes. This one, every half cycle, we call it one loop, like this. This is one half cycle. One loop, 2 loops, okay, and this is 3 loop, and this is 4 loop. So every half cycle, every half a wave, we say one loop, 2 loop, 3 loop, 4 loop. So this one has 4 loop, 3 loop, 2 loop, and 1 loop. These are all the possible patterns that you will see when you vibrate it. Okay, each of them has their own frequency. I repeat, each of them has their own frequency and has their own wavelength, and we are going to learn to calculate it after this. Okay, now the point here I'm trying to make is whenever you take a fixed string, okay, you pluck it, you vibrate it, how many frequencies that you hear? You look at how many possible stationary waves. Here, 1, 2, 3, 4. 4 frequencies that you will hear. Of course, there are many more, but here, looking at this 4 diagram, you will hear 4 frequencies coming at the same time. Not just one. You pluck it, you hear 4 frequencies coming at the same time, and then that frequency you hear, it gives you the sound. Okay, that is the middle C. Okay, so the middle C that you hear is the harmonics of the sound, and I'll explain in a bit what is the meaning of harmonics. Okay, so this is the few patterns of the stationary waves. Okay, now I'm going to go to the next slide. You can take a screenshot if you want. here I have drawn 4 lines. Okay, these are for the 4 types of stationary waves. Okay, so let's draw it in. We're going to calculate to find the frequency for each wave, So the first one is the fundamental, the most basic pattern, like this. Okay, the crest at the middle, we got 2 nodes and 1 antinode at the middle. Remember, the antinode vibrate at twice the amplitude. Okay, so here, this pattern, we call it the fundamental mode. Or there's another name, we can call it first harmonic. Okay, or we can call it natural. It is the natural tone. When you play the string, you are not only hearing one tone. One tone means like just one mode, okay, the fundamental mode. You're actually hearing tone and overtones at the same time. The tone is the fundamental mode, the frequency of the fundamental mode. The overtones are the other stationary waves that is produced. So one single note you play does not give just one tone. It gives the tones and the overtones. It gives all the harmonics to us. Okay, so this one, if I look at the wavelength, if I want to calculate the wavelength, what is the wavelength here? Okay, we take the length of the wire, whatever is the length given here. We know that length, how many waves can be fitted here? This length, this is half a wave, right? Half a wave. So length equals to half lambda. Okay, half lambda. Okay, if half lambda, then I can say lambda equals to 2L. Okay, let's put this aside first. Now, frequency. We know that frequency from the wave, V equals to frequency into lambda. So if I want to find the frequency of this fundamental mode, then I take FV over lambda, and lambda I put in 2L. So V over 2L. This gives my fundamental frequency. I will call it F note. That is the basic tone, the basic frequency. Okay, what is this V? What is this V? You see, okay, I know V is velocity, but velocity of what? Since the wave is not moving, it's stationary wave, then what is the velocity for? The velocity is for the progressive waves that is traveling in the string. I repeat, the velocity is for the progressive waves that are traveling in the string. What you see here is the stationary waves. It is the effect of the 2 waves that are traveling in the string. So this velocity is actually referring to the moving waves in the string, not the velocity of the standing waves. Okay, not the velocity of the stationary waves. Yeah, so meaning that this one is referring to the wave that you created when you plug it, and also the reflected wave. They both have the same velocity. They must have the same velocity. Otherwise, they cannot create these standing waves. They must have the same V. They must have the same frequency. And they must have the same wavelength. How do you create all this same? The best way you create 2 waves that has the same frequency, wavelength, and speed is by reflection. That is the best way to create it. Okay, now, okay, so frequency equals to this. Okay, we put it aside first. We go to the next one. Okay, the next pattern or the next stationary wave that will form is one complete wave like this, right? Okay. One note 2 nodes at the side, and 2 antinodes in between. Okay, so this one, we call it the first overtone. First overtone. So the tone is the natural one, right? This one step up is overtone. Okay, or we can call it second harmonic. Okay, now given the length L, we know that L equals to this. How many waves can be fitted in this length of wire? This is one complete wave. So L equals to lambda. Frequency equals to V over lambda. So frequency equals to V over L. Now I can make this F equals to 2V over 2L. Let's put this aside first. Okay, it's the same thing. I did not change anything. I just put 2 and 2 here because I want to make comparison later. Let's put it aside first. Okay, now let's go to the next one. Here, the third pattern, this is 1.5. Okay, 1.5. So no need to memorize all this pattern. Actually, yeah, you just you draw the wave like this, like how I did just now, and then you just take the node to the next node, to the next node, to the next node, to the next node. Okay, you can use this to help you to draw out the pattern. Okay, so here we have node, 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 antinode, antinode, antinode. Each loop, they are going up and down. Okay, up and down. All right, this one we say second overtone, or we can say the third harmonic. What is the wavelength? L equals to 1 wave and half a wave, so 1.5 wave. That is 3 over 2 lambda. So I move it, lambda equals to 2L over 3. And I put it in the frequency. I get V over 2L over 3. So that is equals to 3V over 2L. Okay, so let's box this. Let's go to the last one. The fourth one, 2 waves, 4 loops, like this. 3 nodes in between, and 4 antinodes in between. This is the third overtone, or the fourth harmonic. Okay, now wavelength, again, we find it by looking at how many waves in the length. 1 wave, 2 waves, so 2 lambda. Lambda equals to L over 2. Okay, frequency equals to V over lambda over 2. So that is 2V over L. Now this one, I can put it like this. 4 times V over 2L. It's the same thing, right? So by putting the 4 in, you times this one, you get the same thing, 2V over L. Okay, so why do I want to make it like this? Because there is a pattern that you will see for all these vibrations. From the first one, the fundamental frequency, okay, the basic frequency is V over 2L. For this one, I can express like this. This is F equals to 2 V over 2L. What is this? This is your fundamental frequency. Okay, so meaning that I can put it as 2 times of the fundamental frequency. Same for this one. The 3, I bring it out. The V over 2L is the fundamental frequency. So this is equals to 3 times the fundamental frequency. And for this one is 4 times the fundamental frequency. So as you go up 1 tone, first overtone, second overtone, third overtone, what is happening to the frequency? The frequency become twice of it, 3 times, 4 times, 5 times, 6 times, and so on and so forth. You can find the next one, the 5th harmonic, the 6th harmonic, the 7th harmonic, and all the frequencies, it is increased in integral. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so what does it mean? What does all this mean? Meaning that when you plug the string, let's say you take one string and you plug the string, and the string's fundamental frequency, F note, based on the length of the string, because you can see this formula is based on what? The velocity and also based on the length, right? I can adjust the length to get the basic frequency. If I play the note, I play the string, it gives me 100 hertz. Just an example, 100 hertz of frequency. I hear a pitch, right? I hear a certain tone. This is 100 hertz. At the same time, all this, the first harmonic, the second harmonic, the third and the fourth harmonic, all these come to me at the same time. At the same time. Okay, when you plug the string, all the harmonics come to my ear at the same time. But the loudest is the first one. The fundamental mode is always the loudest. Meaning that the one that you hear the most is the frequency of the fundamental mode. But the first overtone, the second overtone, the third overtone is also there. It's also there. You are hearing it. Okay, but the fundamental mode is the loudest. It has the highest amplitude. Okay, so that is why I said the sound that you hear is actually a set of frequencies. What frequencies? If you play the string gives you 100 hertz, then you are hearing 200 hertz. That is the first, that is the second harmonic. You are hearing 300 hertz. That's the third harmonic. And then the fourth harmonic, you are hearing 400 hertz. You are hearing 500 hertz, 600 hertz. All these come to you at the same time. So this package that comes to you, we call them the harmonics. Okay, the first harmonic, second, all that. We short it as harmonics. Okay, so let's say if I want to hear this one louder, let's say I want to hear this one louder. Now, when I play the string, right, which one I hear the loudest? The fundamental mode, right? The fundamental mode, loudest. If I want to hear, let's say I want to hear the 200 hertz louder, what happened? I have to create a note in the middle. I have to create the second harmonic. How do I create it? I create it by pressing the string on the guitar neck, the fretboard. By pressing the string on the neck, what happened? I have created a note in the middle. that is the same as this second stationary waves. So by pressing the string on the guitar neck, I can create the second harmonic. I can hear the 200 hertz louder. Okay, so by doing that, I have changed the pitch because initially it's 100, right? 100 is the loudest. By pressing the middle, I create this note. Then now I'm hearing 200 louder. The pitch change. So it's like you press the string, then you hear a high pitch, higher frequency, thinner sound, and higher pitch. Okay, let's say I want to hear even higher pitch. Then again, I press here. So the length becomes this one, right? I press here, the distance of the string from where I press and from where I play it, okay, to the body, the string to the body of the guitar, right? It can be organ as well, or piano, any strings instruments. When you press it, you are decreasing the length, okay? You are decreasing the length by creating a note here. So what happens when you decrease the length? Then you hear this one, 300 hertz, loudest. The pitch has changed. Again, it increase in pitch. I decrease even more. This one, the length is over here. Only this. I hear 400. I hear 400 hertz. So I keep hearing the harmonics of the fundamental frequencies by changing the length on the guitar board. I hear the integral frequencies. Understand? Okay, so you see, if I want, how about if I want to hear, okay, this one I can hear 100 hertz, I hear 200 hertz. These are all the harmonics, right? What if, let's say, I want to hear 120? What happened? If I want to hear 120, can I create 120 based on this one? I can create 120 if I change the basic frequency by decreasing the length of the wire, by decreasing the length of the string. If I decrease the length of the string so that the frequency fundamental is 120, then what frequency do I hear? When I play it, I will hear the integral multiple of the fundamental frequency 120, meaning that you will hear 120, you will hear 240, okay, and you will hear 360. This go on and on. All this, they are the harmonics of this fundamental mode, because you have changed the length of the wire. The fundamental frequency has changed. When you play it, you hear a whole different set of frequencies that are the harmonics of the fundamental mode. Okay. Now, you see here, how about if the question asks you, okay, so far, okay, what is the bottom line? The bottom line is the frequency that you need to know. When I go from the first harmonic, second harmonic, third harmonic, and fourth harmonic, what happened to the frequency? The frequency goes F note, 2 F note, okay, and then it goes 3 F note and 4 F note. Okay, increase in integral like this. And the formula also you need to know, the frequency formula, this one, because the frequency formula is different for each harmonics. Let's say I'm getting the third harmonic, calculate the frequency, then you have to use the third harmonic frequency. Or if you have the frequency fundamental, you can just times 3, okay, to get it. How about if I want the 23rd harmonic? What is the frequency of the 23rd harmonics? Of course, we are not going to draw 23 diagrams here, so we are going to use a formula. You can see a pattern here because F0, 2F0, 3F0, 4F0. So if it's 23rd, then it's 23rd, 23F0. Okay, 23F0. So you just find the fundamental frequency, you times 23, that is the 23rd harmonics, the frequency. So we can make a general statement for the nth harmonic. We take n times the fundamental frequency. This one is another one. So n into the fundamental frequency. Or we can say, continue here, nth harmonic equals to n, and then we put the formula v, nv over 2l. Okay, so this is from the equation of the fundamental frequency. Okay. Any question? You can take down. You can take this down. Okay, so we are going to take like a 3-minute break, and we will continue after 3 minutes. Okay, I need to take a toilet break, so I'll be back in 3 minutes. Okay, let's continue. Right, let me erase this one. Okay, so we know that the fundamental frequency F naught equals to V over 2L, right? Okay, what is the V then? The V is expressed as equals to the square root of T over mu. Okay, what is the mu and the T? The T is tension. Because if you want a string to vibrate, you're going to need a certain tension. Okay, so that is the tension of the string. And this mu is the mass per unit length. Mass per unit length. This formula is applied on strings. Okay, so the mass per unit length, meaning that if you have a wire here, then you calculate 1 unit of length. Okay, it can be 1 meter or 1 cm. How much is the mass? That is mass per unit length. Okay, so the unit is in kg m minus 1. Okay, so put the V in. What do we get? F naught equals to 1 over 2L square root T over mu. So this is another one that you may need to remember. The fundamental frequency depends on the length of the wire, the tension of the wire, and also the mass per unit length of the wire. So if I want to increase the pitch of a guitar strings, what do I do? Based on this one, there are 3 factors. First is the length, right? So I can decrease the length by shortening the string, by pressing the fretboard. Okay, by pressing the string, I have created a note and I have shortened the string. So I have changed the frequency that I hear to higher pitch. The second way is by increasing the tension, right? By tightening the string. Or I can also play the thinner string. Okay, if I play the thinner string, then I get a higher pitch because thinner string has a smaller mass per unit length. So thus the fundamental frequency will increase. Everything that you vibrate, regardless of the length, okay, everything that you vibrate, it will have its own fundamental frequencies. Okay, it will have its own fundamental frequency. And what we are hearing is not only the fundamental, we are hearing the harmonics as well. Huh? So 2F note, 3F note, 4F note. Okay. So sometimes I can connect these strings. Now for a fixed strings, we have 2 notes end to end, right? Sometimes I can replace one end to a signal generator. For example, okay, I can connect my string like this. You see, I take a pulley. One end I connect it to a frequency generator, a vibrator. Okay, so this is frequency generator, meaning that I can make it vibrate at any frequency that I want. And here at the end, I attach a mass, a weight, W. Now, question will ask you, what's the reason of the W? Why do I want to attach the weight here? This is to provide tension, to provide tension. So we attach a weight here. Now, by passing the string over the pulley, this is the string, we have created note here, And also we have created node here. And sometimes, depending on what type of connection is here, if the connection is a fixed connection, then it is a node. If the connection is allowed to swing up and down, then it becomes an anti-node. You have to be careful with that one. Okay, but seldom they will ask you lah. But just for the sake of knowing, okay. So when this go up down, if this is allowed to go up down, then this become an anti-node. Okay, because you can never have moving as node. Node means cannot move. So if the vibrator is going up down, then you have created an anti-node at the end. So if you have created an anti-node at the end, then the whole pattern changes, right? If this is anti-node, right, then what is the stationary wave here? Is no longer like this. No longer like this. This is for two nodes at the end. Okay, it becomes like this. Okay, very easy. You just do the wave and then you put in all the nodes. This is first node, second node, third node. Where is the anti-node? Anti-node is here, here, and here. Okay, so since this n is node, then you ask yourself how many waves I can fit. I can put in between a node and an anti-node. This one, this and this. So meaning that your string is like this. This is your first mode, like this. Go to the next one, this one. So your second stationary waves would be like this. Go up, down, and then like this. Stop here. Because this point is allowed to move. So it is an anti-node. It must be an anti-node. So here is node, here is another node. This one, node, here is anti-node. So you can see here, depending on whether I fix the point at the end or I allow it to vibrate, that changes the stationary waves that is produced here. Okay. Now, so this signal generator, I can vibrate the string at any frequency I want. I can set it to the fundamental frequency of the string, right? We have worked out the fundamental frequency of the string. If I have two fixed n, the fundamental frequency is equals to V over 2L, right? And the pattern is like this. So if you set the fundamental frequency, you set the generator to this frequency, then you're forcing it to vibrate like this. Okay, so if I make it twice the frequency of the fundamental, then I get what pattern? I will see that it become like this. Okay, all this it can be done experimentally. You do the twice frequency 3 times, you get the next and the next and the next pattern. Of course, you have to first know what is the fundamental frequency of the string, and you can know that by using this calculation, right? Of any strings. Okay, so this setup is to study stationary waves, and by using a vibrator, I can force a given mode. I can force the string to vibrate at a given mode. First harmonic, second harmonic, third or fourth harmonic. Okay, so this sums up the key things. Okay, I would say the key things that you need to know in the stationary waves in strings. And after this, I will show a few examples and we'll look at the exercises. Okay. Okay, let's look at example number 1. Wait. Okay, example number 1. A stationary wave is set up on a wire of length 0.93. Okay, length, this is L, so that it vibrates at 120 Hertz. That's the frequency. The fundamental frequency of the wire is 40. So it's given here, F naught, it's 40 Hertz. Draw a sketch of the stationary wave obtained. So meaning that draw the pattern. How do you know the pattern? Okay, you see the wave is, the string is vibrating at 120. So 120, the fundamental frequency is 40. So if we take 120 divided by 40, 0, that is 3 times. 3 times of my fundamental frequency. So you know that it is the third harmonic. Okay, so A, third harmonic means that you have three loops, right? So then you draw it. Okay, you draw the string. I have 3 loops. 1, 2, 3, with 2 notes in between, and then 3 antinodes in between. This is the third harmonic. The third harmonic is, okay, the third harmonic is what? What mode? Third harmonic is second overtone. Okay, so third harmonic, second overtone. B, calculate the speed of the wave. Okay, calculate the speed. B, we can do the general formula, frequency into wavelength. But first, you have to get what is the wavelength. Frequency we already have, right? 120 Hertz. So the wavelength for the third harmonic is equals to 2/3 of the length. Okay, so 2/3 of the length, we have 2/3 times 0.93. 0.62 meter. So put it in, we have V equals to 120 times 0.62. then ms minus 1. OK， 这个 velocity 是什么？谁的 velocity？ 这个是那个 progressive wave 的 velocity， the reflected wave and also the incoming wave. It is their velocity. Okay, example 2. A signal generator is set at 152. 10 loops fit the length of the vibrating string, or vibrating length of string exactly. Okay, the string is of length 2.0 meter and the mass on the end of it is 0.72. Okay, so this one I connect to a vibrator, assuming that 2 points are the note. I get 10 loops. Okay, 10 loops, and calculate the mass of the string. Okay, how do we start? Mass of the string. So I can use what? The velocity formula, right? The velocity formula. Okay, so from here, velocity equals to T over mu. And also I know velocity for speed is equals to F lambda. Now, if you want to calculate the mass of the string, you need to know this one. Okay, so all I need to do is to find what is the V, what is the T. The T is already given. Then I can find the mu. Okay, the mu is mass per unit length. Okay, from the V, I find it from F equals to V equals to F lambda. But this lambda frequency is 152 hertz. How about the lambda? Lambda, you have to know at which harmonic it is vibrating. So 10 loops, that is the 10th. Okay, that is the 10th harmonics. Okay, so we can use the formula for nth harmonics equals to what? And V over 2L. Okay, for the 10th harmonics is 10 times the frequencies. Okay, so 10V over 2L, that becomes 5V over L. Okay, 5V over L. So meaning that we take the wavelength, the wavelength is the length of 2 loops. So 2 over 10, and then we times by 2 meter equals to 0.4 meter. Okay, that is the wavelength, 0.4 meter. So 0.4 meter goes here. Times it, you get the velocity. Equals to, velocity is 60.8 ms minus 1. Okay, put it in here. Then we get 60.8 square equals to, tension is 0.72 times, okay, I use 9.81 divided by the mu. (1.9) times 10 power of negative 3. Okay, now don't forget this one. This one is kg/meter. So to find the mass, you times by the length. 1.9 times 10 minus 3 times by 2 meter. Okay, so the final mass is around 3.8 gram. Change it to gram. It's a very small number. Okay, next one. Okay, you do this. 3 and 4. Try it first. Later, I'll show you the answer. Okay, so we have length 0.6, velocity 600. What are the three lowest resonant frequencies? Meaning that the fundamental, the second harmonic, and the third harmonic. Okay, we have the V, we have the L, we can find it. So fundamental equals to V over 2L, 600 over 2 times 0.6. 500. So fundamental is 500 hertz. Second harmonic is twice of this, right? So you just times this, 1000 hertz. And this is 3 times of this, 15,000. So 1, 2, 3 is your answer. The lowest resonant frequencies. Okay, resonant. Why we call it resonant? Because standing waves is actually resonance. Because when they interfere, right, you get constructive interference, twice the amplitude. That is already resonance. Okay, resonant means like you have two waves coming at the same time, at the same phase. So they add up, right? Resonance. Okay. Example 4, which is the last one. A steel wire of mass 5 times 10 to the power of -4 kg and length 0.5 meter is stretched with a force of 88.2. So that's the tension. Determine the mass per unit length of the wire. Okay. Mass per unit length is the mu. So 5 times 10 minus 4 divided by 0.5. That is 1 times 10 minus 3 kg m minus 1. B, the velocity of the propagation of a transverse wave. So the V, we can use V equals to tension over mass per unit length. Okay, so 88.2 divided by, like this, we get 296.98. I'll approach it to 297. C, the frequency of its first, second, and third harmonic. Okay, so first harmonic, the fundamental, V over 2L equals to 297 over 2, 0.5. Two nine seven. This is the first harmonic. Second harmonic, just times 2, huh? 297, 594 hertz. And third harmonic, 3 times 297. (891) hertz. Okay,